Now let's have a look at a system that performs a rather more complex combination of functions than a television. We all know how to use a personal computer. We can access lots of different applications, operating the applications to get what we want, like creating documents, creating diagrams, accessing email, and so on. So we understand the computer, at least in some senses. If we tried to express that understanding of how a computer worked, we might come up with that lower left diagram. Lots of different applications. We can shift from one application to another. We can share information between applications. We can put a photo into a document we're creating. We can attach the document to an email. So we talk about the operating system of the computer that manages shifts between applications, controls the resources available to different applications, and arranges information exchanges between the applications. But if you look inside a laptop computer, there's lots of printed circuit assemblies. Each printed circuit assembly has multiple integrated circuits and other components. One integrated circuit alone can have billions of transistors and other electronic elements. But none of these structures corresponds with any one application. There's no one piece of hardware on any level that corresponds with word processing, or games, or email access, in the sense that it does all the processing for the one application and nothing for any of the others. You can identify different hardware components, but these components have functions like processing, memory, Wi-Fi interface, and screen management. And any one application uses most, if not all, of the different hardware components. And in fact, even at the most detailed level, at different points in time, any one transistor may support any application. So there's a major mismatch between the way a user understands the system and how a designer understands it. And there's a very similar situation with brains. Cognitive tasks can be classified into different types, like memory for facts, memory for events, and memory for skills. We also see major physical components in the brain, like the cortex, the hippocampus, the thalamus, and so on. But we don't find anatomical structures that correspond with types of cognitive tasks. Now, some computer systems are a lot more complex even than personal computers. There are systems that control networks of physical equipment in real time with no human intervention, like the systems that control the internet. But just like personal computers, there's a mismatch between how a user would describe a system and how a designer would describe it. A designer would talk about how the physical resources of the system are arranged in a modular hierarchy. The modules at different levels are transistors, standard cells on integrated circuits, printed circuit assemblies, and shelves of assemblies. Modules perform information processes on different levels of detail. A user will talk about going to different websites, searching, accessing email, and so on. Understanding means we have to be able to bridge the gap between those two ways to describe the system. It also means that we have to design transistors that are fast enough to organize these transistors into integrated circuits, organize the integrated circuits into printed circuit assemblies, the printed circuit assemblies into a system. We have to create software languages that can translate feature designs into fast enough machine code. And all these pieces have to be designed to fit together. Now, let's take a broad perspective on what a control system does, whether it's a personal computer or something much more complex. In the most general terms, it's got to detect conditions in the information available to it and associate those conditions with appropriate behaviors. A computer has to detect that you've entered the address of a specific website and associate that detection with the behavior of contacting the specific website and downloading the page display information. In electronic systems, The conditions, the behaviors, and all the associations between them are specified by a designer. So the associations can be completely unambiguous, which means that condition detections can be associated with commands to perform behaviors, what we call instructions. In the prototypical software line, if condition X equals A is detected, execute the specified instruction. And that leads to computer systems using two general types of information processes to support this overall function: instructions, that are commands to perform behaviors, and data reads-writes, that manage the information associated with the detection of conditions. And in electronic systems, there's actually a major separation between physical structures specializing in instructions and structures specializing in data reads and writes. These two information models, instructions and data read-writes, are the foundation for full understanding of computer systems. The hierarchies of description that link transistor operations to user features are based on the use of these two information models. We can describe the operations of a system at high level and at many more detailed levels, all in terms of the same information models. At a user level, accessing a web page can be described as detecting an address condition and performing an instruction to go to that address. This high-level instruction is made up of sequences and combinations of more detailed instructions. Each more detailed instruction is made up of sequences and combinations of yet more detailed instructions, through software instructions, assembly code instructions, down to hardware instructions that can be interpreted as commands like open the gate of a transistor. In a similar way, data constructs at high level are combinations of more detailed data constructs. This consistent use of the same information process paradigms means we can map between levels. Now, it's true I'm simplifying a bit here, because when you map two high-level instructions to a more detailed level, the more detailed instructions may actually overlap. So understanding isn't trivial, but the key point is that the existence of this mapping makes it feasible to understand how transistor operations ultimately support the features of the system, meaning that we can design consistently on every level. So these information paradigms make it possible to have the kind of understanding we need if we want to add or change user features, manufacture systems that meet specifications, or identify failed components.